to be here. I hope you're not all too exhausted and at mental capacity. But in anticipating that you might be, I also decided to follow Ottmar's lead and try to lecture most of the time at a relatively casual pace. And at the end, if I have time, I'll talk a bit more about some of our recent research, just previews. What I wanted to talk today is a topic that I think is very interesting and very important, which is when we design visual learning algorithms, how can we design them or implement them such that they know when they don't know something, okay? But let me start off by simply stating the obvious. We all know that when we do scene analysis with computer vision methods these days, we use these things, deep convolutional neural networks, like this one here, which is by now almost historical, right? So for image classification, which is only one of many tasks, we design a network with many layers to give us the classification output. And how do we train that? We train it discriminatively for a specific task at hand, okay? And that works so successfully that some people sometimes get tempted into saying, oh, this problem is solved, okay? I don't want to debate that for now, but I want to also mention that actually CNNs, even the good ones, even if they're trained carefully on data sets that we've a lot of experience with, they do make mistakes. So for example, all convolutional net on Sci-Far 10, this is clearly a horse. What does it tell us? It's a bird. Okay, not correct. What about this one? That seems like an airplane, yet the network says truck. Okay, and at this point you might say, okay, I know what he's been doing, right? We all know about these adversarial examples, right? As has been discussed many times, it's possible to add a small level of input distortion to fool the network into giving a completely incorrect prediction. And there are many methods in order to achieve that, and also a lot of research trying to protect against that. But what I want to talk about here is the non-adversarial case. Fully acknowledging that this is a very important problem, but even in the non-adversarial case, we actually have this issue. Okay, so CNNs make mistakes. That wouldn't be so bad in some sense if the CNN at least knew that it might be onto something incorrect. But if we actually look at what the output is, it's not this label really, right? Because how we train a CNN is to actually give us a distribution over the target labels. And the distribution in these two cases looks like this. The network says, with probability 1, this is a bird, and with probability 0, it's any of the other classes. Virtually 0, anyway, okay? And this is an important problem. The network is wrong, and yet it's really, really sure that it's correct, okay? So, the question is, of course, is this a general problem? And there's a very interesting analysis by Guo and colleagues from ICML 2017, which looked at calibration errors in modern neural networks across a variety of different data sets. And one of the things that they found is if you look at the entire data set and you graph how confident is the network in each of the predictions on all of the data items, you find that large amounts of the mass, does it work? Yes. Large amounts of the confidence is concentrated at 1. Okay? So the average confidence is something like 0.9, whereas the accuracy on that particular data set is only 0.7-ish. Okay? So, and you would kind of hope that these two agree, otherwise your confidence is somehow not a good predictor of how much you can actually believe in your prediction. And a different way to look at the same is to graph the confidence against the accuracy. So what you see here is if the confidence were to correctly reflect the accuracy of that particular type of data, then we would be on this diagonal. Yet the actual histogram over the confidences falls well below that. Okay, so we generally tend to be overconfident, and these medium confidences for things where we actually make mistakes, they seem to be incorrect. Okay, so the first question is, why is this problematic? Right? You might say, oh, well, so be it. As long as it classifies correctly, I'm fine. But there's a number of problems, I would argue, that are associated with it. if you've been to NeurIPS and you saw the keynote by Spiegelhalter, he argued that very eloquently, and I think the video is online. If you want to watch it, I highly encourage you to. He talks about uncertainty and how it relates to building AI that people, like lay people, can actually trust. He argues outputting proper uncertainty is a very important thing. Another important reason is the open world problem, I would say. So if you want to build, say, an autonomous car, and you want to design a scene understanding network that correctly understands what's going on in front of it, you can't possibly build it for all object categories that might occur to you. So for example, someone might have lost their suitcase on the road, yet in our normal data sets, the category suitcase isn't baked in because, in scene understanding of road scenes, that doesn't happen all that often, but that doesn't mean that it doesn't happen at all, okay? So there's a whole community interested in this problem. How do we go from standard multi-class classification to what's called open set recognition, where you have a bunch of predefined categories, but then other things may come along and you want to deal with it in a graceful way. And another important motivation from my perspective is also that of modularity. Yes, we do a lot of end-to-end training, but not for everything do we have sufficient data available. And so sometimes it's very good to be able to compose a system out of different parts. One application, for example, is tracking, where often you use an off-the-shelf object detector, and then you want to combine that and do some temporal reasoning, and you train them independently. Okay? And if you then can't rely on the confidences that's output by this detector, that's a bit of a problem. Okay. So why are these confidences incorrect? So let's look at how we train those. As most of you surely know, the standard way to train a classifier is to actually take the activations from the last layer that are unconstrained and convert them into class probabilities. And the way we do this is using the softmax. So we just exponentiate them and normalize by their sum, and that's it. Okay. And then when we train, what we train is basically what we maximize is the log likelihood of these activations. So we compute the cross entropy between the empirical distribution and the class probabilities. Okay. So you might say, well, we seem to be doing the right thing. Looks okay, right? Because we actually look at the class probabilities, and hopefully they should reflect the correct distribution. And if that's the case, then our training objective is in good shape. Okay. And by the way, it's important to recall that this is nothing new, right? Neural networks have been invented before, well before the current wave that we're seeing, and they were trained like this back then. So we can ask the question, why didn't anyone actually notice this before? Okay, is there something new? Question.
I mean, did they not? There was like flat scaling and everything to better calibrate SVMs and such.
Right. Okay, that's a very good point. We'll get to that. So yes, there's been definitely problems in scaling with other types of classifiers as well, and people have tried to come up with better ways of doing calibration. But somehow in the neural network world, this has not been applied as widely. Okay. So what Gu and colleagues say in their very nice analysis is that, this is the same diagram that I showed you before. One important thing that I haven't revealed to you about it is what network is it? Okay. That turns out to be a ResNet on Sci-Far 100, whatever. On a different data set, it would be roughly the same thing. So is this a new phenomenon? Interestingly, somehow it is, because if you look at a classical network from the 90s, LeNet, for example, on the same data set, it doesn't exhibit this problem. So the confidences are very evenly distributed over the whole range from 0 to 1. And if you look at this calibration error plot where you plot confidence versus accuracy, it seems to closely follow the diagonal. Okay? Question?
Is this actually on the training set or on the test set?
This is on a holdout set, yes.
So would we get the same thing on the training set?
On the training set, the effect is even more pronounced. I'll come to that on my next slide, I think. Yes?
Is this like the original LeNet with like sigmoidal saturating nonlinearities, or is this the like kind of modern style with non-saturating?
That is a good question that I cannot answer off the top of my head. I would need to look at that. But as far as I understand, the sigmoids or the nonlinearities did not seem to play an essential role in that conclusion. That's my recalling. Okay, so why does this happen? Why does it happen now with our ResNet and it didn't happen with LINET? So one of the things that they found is that this calibration error is strongly dependent on the depth of the network. So first of all, how do we define the calibration error? Basically what they say is some of the confidence of a particular sample should somehow be related to the accuracy that you could expect if you were to observe multiple instances of that example. Okay? So accuracy and confidence should be similar, and if they're not similar, you penalize that, it gives you an error. And the accuracy, well, is defined as you would expect. You simply count how often you're correct, and for the confidence, you simply sum up the confidences of all of the examples. Okay? And what you then find, as you increase the network depth, as expected, the error tends to go down. This is a test or validation error, but the calibration error actually goes up. Okay? So why is that the case? What they argue is basically that because the network has more capacity, it can spend a lot of its energy, if you will, on optimizing the cross entropy. And so it basically optimizes getting, so if you recall that objective that we had, it basically optimizes, since these are 0, 1, so these are the target categories, or the target outputs for the different categories. We're trying to push the sigmoid, the softmax output as close to 1 as possible to basically optimize this objective. And because the network has so much learning capacity, this seems to happen, especially if we have deep networks. Okay? And a similar trend happens when you actually vary the width, add feature channels, you have more capacity, you have more chances to optimize the likelihood. And by the way, why does that not reflect on the accuracy? The accuracy has already saturated. And but you're still optimizing the cross entropy, and so you're making this miscalibration thing worse and worse. Okay? So now I forgot to answer the previous question. What was the previous question that I want to come back to? Oh, right, test and validation. So training and validation error. On training, this effect gets even more pronounced because it tries to push the cross entropy even more and has a lot of capacity to basically push up the softmax outputs for the training data. But it turns out, even if you look at validation or test data, this trend continues. Now that's the thing that's relatively easy to interpret why that might happen. Less interpretable does it become when you look at other factors. One thing that they find is that batch normalization seems to also have adverse effects on this miscalibration problem, and also the lack of weight decay. So that's maybe, again, somewhat interpretable. So if you have little weight decay, you get a lot of miscalibration. If you use weight decay, meaning regularization, then the miscalibration error goes down. But in recent years, weight decay is used less and less, and this is also one of the reasons why we seem to be observing this problem more and more. Okay. So that's a problem. Problems are good. Let's see what a solution might be. The simplest solution that they propose is actually very related to also rescaling approaches that were used in classical classification methods like SVM. What they found worked the best is a simple, what they call temperature rescaling. So you basically just take the same softmax and you make this innocuous change that you divide the activations before the softmax by some temperature. That temperature, of course, needs to be tuned. You take the validation set, not the training set, of course, to do that, and use the log likelihood to tune it. Very simple. And an important component of that is it doesn't actually change the accuracy because the winner is still the winner. It's just that you change its confidence. Yes, question?
In their method, is the temperature like a shared constant across all data, or is it actually an output of the network?
No, it's a shared constant across the whole network. But of course, you might imagine also adapting that.
Yeah, because I've seen results for that something like robustness during training, but I haven't seen like a calibration evaluation of it. So have you seen anything like that?
For changing temperature per data item, no, I haven't seen a calibration evaluation of that. Yeah. Yeah. So it doesn't change the accuracy, right? That was my point, because the maximum will, or the argmax will still be the argmax, even if you change the scaling here, but you affect the calibration. Does it help? Quite a bit. So here is again the previous result, the same ResNet that we saw before. What happens to my pointer? The same ResNet that we saw before, where the confidences were significantly biased towards 1 and below the diagonal. Whereas if you apply the temperature scaling, you get very close to the diagonal. So the confidences for the respective types of data are very closely aligned to the accuracy that you would achieve on them. Okay, and they also did a very extensive analysis on different methods, also different kinds of classical vector and matrix scaling methods where you learn additional parameters, and adaptive binning methods and whatnot. But they found basically that through the board, and these are various different networks, as you can see on a number of different data sets, including large-scale ones like ImageNet, they found that this temperature scaling method actually performed very well. Okay, so I guess what I want to get across in this first part is that it's an important problem, and there's actually, at least for the classification, there's a very simple solution that's very easy to try, very simple to implement, that already helps to some extent without actually negatively affecting the predictive performance of your classifier. Okay? But then, classification is not all, right? There are a lot of tasks in computer vision where we don't actually do classification, we do regression instead. So for example, motion estimation, we take 2 or more frames in, we want to estimate the motion of every pixel and output an optical flow field. Or maybe we want to do some 3D reconstruction, we give it an image or multiple images, and we want to, say, get a voxel representation or something of that sort. Or image restoration, we take a very blurry image in and want to have a nice image out. Okay, all of these are regression tasks where we're not trying to do classification. There, the situation, I would argue, is even worse because there are actually no probabilities in the deep network at all, no uncertainty. Because what we do is we simply regard the output from the last layer as the output of the network. That's the regression output that we try to fit. And what objective do we use? Very frequently, we use the L2 error, the sum squared errors, where we have some target value, say some target motion, and we have some output from the network. We penalize that squared error, and that's it. Okay, so there is no notion of uncertainty at all. Yes, question?
Does that assume that the output is a Gaussian, has a Gaussian noise around the true value?
Okay, so that's a very good question. Does it assume that? And I would argue yes, and I'll get to basically, in some sense, a better version of that in a moment. Yes, but it's correct. By choosing some loss function, you in some sense assume something about the distribution of the outputs. And because of that, because that's not a very robust distribution, that's also not necessarily also the best error function or loss function that people use for training. In fact, for example, for motion, people found that this, formally speaking, L2-1 loss is the best, where for every output vector, you compute the Euclidean distance, and then you sum them up, as opposed to the sum of the squares. And that turns out to be more robust and is more appropriate for things like motion estimation, depth estimation, and so on. Yes, question?
But the mean isn't a complete Gaussian distribution either, right? Like your network could output a mean invariance, like people do in reconstruction.
The network could output...
kind of robustness.
Yes, so I'll get to that. Yes. Yes. Okay, so in a typical regression network, 99% of what we see in our community, that's what people do. They just take a network as a function approximator and penalize the output or the distance to some target value with some loss function. Okay, they're typically from the LP class. So what I want to point out here is that when we regard the network like this, we can think of it as deterministically transforming from the input to the output layer by layer. So at the input, we observe a certain value. And if we think of observing a certain value, one way to think of it is we have a distribution that's entirely centered on one specific observation. So it's like a Dirac delta that's on the input that we observe. Then we feed it through some layers, a linear layer and a ReLU nonlinearity, and then it's again a deterministic value. It's a simple Dirac delta again someplace else, and so on. Then we continue, and at the output we again have a deterministic value. It's like a distribution that's centered on one specific output. So all of the layers, the input as well as all of the subsequent layer activations are completely deterministic. Okay? But I would argue even in this realm of continuous prediction, regression, this is not ideal. So here's a motion estimation task. Here's some input frames. They're overlaid, so both the input images are overlaid. Then you see the ground truth with the color encoding, where the color gives you the direction of motion and the saturation gives you the velocity of it. And then you see the prediction of an off-the-shelf network. Okay, that's not the state of the art, so don't take that as representative of that, but I just want to illustrate the basic problem. And of course, there is some deviation of the ground truth and some errors, especially near the boundaries, for example, and you'd kind of like to know where they occur. So could the network assess itself that in certain areas of the image it's less certain than in others? So can we know when and where the network fails? And that's useful for a number of things, inspection and also downstream modules, right? Optical flow is very rarely the actual output of a computer vision system, but it's one feature that we use for something else very often. Okay? So I want to ask, can we get uncertainties in regression? And in some sense, I would like to ask, can we get them back? Because it's not like we've never had them. In the good old days, we didn't use deep networks, but we used something like this, Bayesian networks, Markov random fields, conditional random fields. And while the community didn't always do the best job in necessarily taking their probabilistic interpretation very seriously, nevertheless, it's a very well understood theoretical framework for modeling dependencies and uncertainties. We have a very powerful standard library of algorithms for learning and estimation, and it's been applied to basically any problem in computer vision. But it's fallen out of fashion because, of course, these models don't have the learning power of deep networks, and so we don't seem to be using them anymore. However, nothing stands in the way of trying to combine the benefits of these and deep networks, and so one can, I would argue, and should think about probabilistic deep networks. But at least in the computer vision community, they don't seem to have found a very widespread use yet. So what I want to basically talk about in the next half hour or so is whether we can combine the advantages of graphical models with deep networks. And like with many things in the history of deep networks, this is somehow not a new question. In the 90s, it turns out that many people that we know very well, like Jeff Hinton, have thought about this problem. So for example, Brandon Frey and Jeff Hinton had this paper, Variational Learning in Nonlinear Gaussian Belief Networks, what that really tries to get nicely calibrated outputs in the generative setting, I should say. And David Mackay has also worked on this problem in the 90s, and he even, if you read the abstract, he even wants to do a full Bayesian treatment of the different model architectures. So something that we would regard as extremely ambitious today was on people's minds in the 90s already. Okay. Yeah.
Like the networks like Pixel CNN. So I think in the generative modeling framework, those need to be calibrated very well when you're
okay. Okay. So Matthias correctly points out in the generative world, probabilities play an important role, and they're very well calibrated. That's absolutely correct. I haven't said this explicitly, but I'm talking about supervised learning here. And because this is sort of the dominant paradigm of most of what's going on in our community. But of course, generative modeling is very important. It's also very dear to my heart. But I wanted to talk about supervised learning here. Okay, so before we solve that question, one thing to think about is what does uncertainty even mean? And there's this very nice analysis from Kendall and Gall, NIPS 2017, about what uncertainties in computer vision arise and what we might want to do about them. And they basically divide the uncertainty that we have in networks for computer vision tasks into two things: epistemic uncertainty, which is basically the uncertainty of the model, or if you think of it just as a neural network, the network parameters given the training data. So in a semantic segmentation example, say in this scene there's a certain ground truth, the network outputs something that's a bit different from it, and hopefully the network knows that maybe that sidewalk has a texture that I haven't really seen very closely. And so in that area where the network is making a lot of mistakes, hopefully it should know that also the uncertainty in that area is relatively high. Okay? So what they conclude in their article, that epistemic uncertainty is very important, particularly for the mentioned out-of-sample setting that I had in the beginning, the suitcase example, and also in the small data setting where I don't have a lot of training data to explain away that uncertainty. Okay? So that's one type of uncertainty. The other type is the so-called aleatoric uncertainty. That's an uncertainty of the model output that relates somehow to the input, to noise in the input. So for example, for the same scene, again, image, ground truths, output from the network, the aleatoric uncertainty is basically related to, because my camera has a certain limitation, it gets noisy if my illumination is poor. I'm also a bit uncertain about where to exactly draw the segment boundaries in this example. Okay? And that, they argue, is also very important to take into account, specifically in the large data setting, where in many of the applications we actually live. Okay? Where we have lots of data, we can reduce the epistemic uncertainty to a large extent, but that uncertainty doesn't go away because our observations are always a bit noisy. Okay? So even with the best of cameras. So despite that importance, in our community somehow this hasn't gotten any traction, but it's not like no one is working on this. In the machine learning community, people are working on that. They are developing all kinds of Bayesian deep network algorithms. But one of the problems is that they tend to be computationally very challenging. At the very least, so in pure Bayesian deep learning, what you regard is not only some of the activations or outputs as uncertain, but also the neural network parameters themselves. And that means you double the memory, right? Because for every parameter, you not only need its parameter, but also at least a variance around it. And for this reason, in our community where we're already exhausting our GPU memory with the networks that we have, no one wants to spend twice as much memory for weights. Okay, so that's one problem. And then it's also relatively slow, and so the uncertainties are largely ignored, even if they're quite useful. But it turns out they can actually be taken care of. So one of the things that was proposed some years ago by Yaron Gal and Zubin Garamani is, they call it MC dropout. I would call it test time dropout, basically the same thing. The basic idea is, ultimately, at the end of the day, if you have a Bayesian neural network, what you would like to do is you would like to take the predictive output from the network, so the distribution over the outputs given the inputs and the weights, and now you want to integrate over the different weight instantiations if you have some uncertainty over what the right weights are. Okay? The big problem in that thing is that there's millions of weights, and you don't want to integrate in a million-dimensional space. So you need to approximate this. And what they find and argue is that there's a very simple way to approximately do this, which is to basically reuse dropout. Now, not for a training method, but rather a test time. So you run your network not only once, but on a specific input x star, you run it L times, and each time with a different dropout instantiation. So you have the typical Bernoulli random variables, you drop out activations, and then you get the output, and you try to get a distribution over different outputs from these L different dropout instances. Okay? And they even they have a very compelling theoretical argument, and it turns out the dropout before every layer, weight layer, can be understood as some form of a deep Gaussian process, so a proper probabilistic model.
What is a dropout?
Dropout is basically when you randomly set the activations to 0 with a certain probability. So that's a typical training paradigm that's used when training a deep network in order to basically force the network to build alternative representations to arrive at the same conclusion, and this way it becomes more robust to certain variations of the input. So you reduce overfitting.
Here you use the symbol W. Do you mean that different instances of weights?
Different instances of the weights, exactly. So you want to, in the setting of being able to deal with this epistemic uncertainty that I mentioned, they argue that the best thing would be to, or like in any Bayesian deep network, you want to average over different weights, and you want to regard the weights not as a single point estimate, but rather as a distribution over the weights. But in order to take that into account, you would need to integrate over all possible weights, and that's not feasible. So they basically propose to approximate it using this random sampling at test time. Okay. There's a downside to it, though, is that for every input that you observe at test time, in order to get an uncertainty, you need to run. Sorry, I got my indices wrong. Why is there L and T? Something is wrong here. Okay.
So you've got weights in each layer, L.
Oh, right, yeah, okay, yeah, right, L are the layers, sorry. Okay, L are the layers. So I want to have T different dropout instances, so I need to do T forward passes at test time. Okay, so basically runtime gets multiplied by T. But it turns out it actually works. So there's Bayesian segnet that Kendall and colleagues proposed, which is a semantic segmentation network that gives you uncertainties. And so here you see a different visualization of the uncertainties. One means the network is confident in its, white means the network is confident in its prediction, and dark means the network is less confident. So for example, here the lane symbols that are painted on the road in the rightmost example somehow make the network less confident, and in fact that's also where it tends to mess up. Okay? So with this relatively simple change where you don't need to change the network architecture, you don't need to change training, you just at test time you basically run your network multiple times with different dropout instantiations, you get some measure of confidence that is practical, and it has some useful connotations. So for example, if you look at the uncertainty of the different categories here plotted on the x-axis and the class accuracy on the y-axis, you can see that there's a very nice correlation for the categories that are most accurate, things that are easy to segment, like sky, pavement, and road. The network is also very certain of its output. And in other categories, like bicyclist, for example, where it's more difficult to segment, the network outputs a much higher uncertainty. So that's sort of what you would expect. So there's a strong correlation between accuracy and uncertainty. The model kind of knows when and where it fails. But from a practical perspective, suppose you now want to design an autonomous car, and you want to put in one of these networks, and you need to run it 100 times in order to get a distribution. That's maybe a bit of a problem. Okay, so you don't want necessarily that large slowdown. Okay, so what can we do to make it more practical? Another approach that's been tried in that context are ensemble methods. And they have a number of motivations. One is speed, as I mentioned, and the other is that full Bayesian deep learning requires custom implementations. It's not what's in our typical libraries, and hence people don't use it as much. But we can use all the training methodology that we have and train an ensemble of standard CNNs and basically take different instantiations of exactly the same network that I would always use and use that to gauge the uncertainty. Okay? So okay, now I'm getting in trouble with pronouncing that name. Lakshmi Narayan proposed an ensemble of standard CNNs, NIPS 2016. And what they basically say is you take the same model m times and you train it with different random subsamples of the data. And because of the stochastic process of learning, you get m different weight instantiations. And now you basically treat the output of the network as a mixture of the individual outputs for classification, say. And for regression, you need to do something a bit more elaborate that I'm not going into for now. Okay? So basically, that already gives you better uncertainties, and you don't really need to change training very much. They additionally propose that you can also add in adversarial training, but that's largely independent of this idea of ensembles. Okay? So what's the benefit of that? The benefit is that it actually turns out to work quite well. So these are basically likelihoods, so negative log likelihoods. And so the deep ensembles on the right, they tend to be very good and better than this test time dropout, despite the fact that in this case, the ensemble only consisted of 5 network instantiations. Okay? So as opposed to saying having a 100 times slowdown because you need to run test time dropout with 100 different dropouts instantiations, here you only have 5. But of course that means 5 times the weights, training 5 networks, so it still incurs a certain training and test time overhead.
So these ensembles of network, why are they different from each other? Because the initialization of training is different, or what makes them different?
Yes, because the initialization is different, so you take different random initializations to start from, and then of course you also use stochastic methods for training, and so they end up in practice in different parameter optima. And of course you might also add in objectives to keep a certain weight diversity, but they found that they didn't even need that. Okay, so they just basically trained the network m times. Okay, so that's still expensive. Another method to make that more efficient, and I think you heard about this in the poster session on Tuesday, so I don't want to go into the details of that, is to basically bring that idea of ensembling and compressing it into a single network. So what Ilg and colleagues proposed is basically to take a single network and have that network output a bunch of different outputs that are all supposed to be different but solving the same task. Okay? And the way they train this is basically sort of a winner takes all loss. So you give the network, say, m different outputs. So it has m different chances of predicting what you would like to predict. And you only score the best one. And you additionally need to have some regularization so that within each prediction you actually get some form of consistency. Okay? And that turns out to be and more accurate than independent ensembling because you only need, in some sense, additional model capacity in the last few layers before the output, and in the beginning of the network, in the encoder, you don't actually need additional weights. So it makes the whole thing more compact and also faster because you don't need to run through the network multiple times. The only computational overhead is near the end of the network. Okay, so that's very nice. On the other hand, there's a downside to it, which is you still need to adapt the network. You can't use the same network that you had before. You need to design a custom architecture to be able to give you this ensemble of predictions and then give you some notion of uncertainty. Okay? So what I want to talk about next is some work that we've done to basically give you uncertainties without much additional engineering. So that was our goal. And so we call it lightweight probabilistic networks. So we want to predict the output with its uncertainty also in regression tasks. And we don't want to have much computation overhead, memory overhead, and also not much engineering. We just want to take the well-proven networks that people are using and use them, reuse them, and repurpose them to give us uncertainties. Now, because we don't want to basically use additional memory, we have one limitation, which is that we cannot deal with epistemic uncertainty. Okay, because that would basically necessitate storing variances over the network weights. So we only can work with aleatoric uncertainty. However, in the large data setting that we often work in, that's also a very important class of uncertainty, though by no means meaning that this is sufficient. Epistemic would be even better. Okay? And so there are two realizations of that principle that we looked at. One is actually very old. It's what was mentioned earlier. We can actually predict the parameters of a probability distribution at the output layer. Okay? And that's, so if you think of that diagram before, we always had basically Dirac deltas, meaning deterministic activations, and only at the very last layer we output a probability distribution. Okay? I'll explain it in a second. And the other alternative that we'll look into is basically treating, because we want to deal with aleatoric uncertainty, we treat the input as inherently uncertain, and then basically owe up to that and propagate these uncertainties all the way through the network. And in the following, I'll describe both. Okay, so first notation, recall that what I defined earlier, I defined the network earlier as basically a series of transformations. I take the input in, I feed it into my first nonlinear layer that has some parameters, and then I continue all the way to the last layer L, and then I get my output. Okay, and in the normal deterministic regression setting, everything from the input to the output is deterministic. It's a point estimate. So the first thing that you could do is take a probabilistic output layer. Basically make the prediction at the very last layer of probability distribution. And interestingly, again, mirroring the story, this is nothing new. It was done proposed already in '94 by Nix and Weigand. Okay? But despite the fact that this is a very old idea, other than in the reconstruction community, as mentioned, this principle doesn't seem to be very widely used. Okay? Yes?
Also, if you use a standard network and you train on cross entropy, I mean, since you say if you have no temperature parameter, the network does a very bad job in calibrating these probabilities, but it's still a prop output.
Yes, for classification it is, but for regression it is not. Yes, so that's correct. For classification we do output probabilities, and even if there's a certain calibration problem, that happens, but for regression it doesn't happen. So I'm talking here specifically about the regression case, and I'll come back to classification later.
For regression, you could output the variance or the corresponding disparate parameter for your distribution, right?
Right. So this is exactly what I want to say now. So basically, you can think of the network output as being a distribution, but how do you output a distribution? Well, you output the parameters of a parametric distribution. So you assume that somehow your last layer has some parametric distribution with some parameters, and now instead of predicting only the output value, you predict the parameters of that distribution directly. Okay? So for example, you take a Gaussian, and then you predict the mean and the variance. Okay? So that's the simplest instantiation. One limitation of that is that, of course, as I argued earlier, we don't just always use the L2 loss to train regressors, but often more general types of losses from the LP family. It turns out if you use the appropriate probability distribution, then you can still do the equivalent thing. So if you have an LP type loss, you can basically use this so-called power exponential distribution, which basically looks a lot like a Gaussian, except that then you raise the exponent to some k, and that basically gives you additional robustness if you want to. Okay, and so for example, you can implement these L2-1 losses that I mentioned earlier. Okay, and what you would predict now, as opposed to the output y, as opposed to the output y, you predict the mean output and the variance parameter to the output. It's only the variance for k is equal to 1, otherwise it's only related to the variance. Okay?
How do you get the mu and beta?
So that's basically now your learning target. You train the same network as before, but you double the number of outputs. One output, or one half of the outputs, is responsible to output the mean parameter, and the other half of the outputs is responsible for outputting the variance parameter. Okay? And then, of course, you ask, well, how do you train it? Well, it turns out, like we said earlier, we can use likelihood. So I got ahead of myself. So for the L2 loss, we need to choose, for example, k is equal to 1. We predict the mean and the variance per output dimension and pixel, as I just mentioned, and that means we have twice as many output nodes in the last layer as in the deterministic case, and we have additional parameters if we want to do that, but only in the last layer. So it's a very small overhead. Okay?
What's the supervised signal for beta?
Okay, so the question was, what is the supervision signal? I'll get to that in a sec. Very quickly, so there's very little computational overhead at both training and test time. But what's the supervision signal? It turns out we can train it like we would do in classification. Okay, we just use maximum likelihood, because cross entropy is basically nothing but maximum conditional likelihood. So we take our probabilistic output, the distribution that we give rise to, we feed in the inputs to the network, and then we observe what's the density of our regression targets, multiply those together, and find the parameters that maximize these. But of course, in practice, we take the log, but that's the spirit of it. Okay? So you would just do maximum likelihood training like you would do with a classifier, and now you can also train a regression model to give you probability distributions. Now you might say, well, hold on, why does that work, right? And we had earlier this question, how does that relate to distributional, how does the L2 loss relate to distributional assumptions on the output? So suppose you had Gaussian outputs with an L2 loss. What you do in standard supervised training when you do it in the deterministic case is that you penalize the squared error and you sum that up over all training data instantiations. What you do in this probabilistic setting is that you output both a mean and a variance. So in some sense it's very similar. In the typical standard supervised learning we only output the mean. Now what we do in addition is outputting the variance, and we don't have ground truth for the variance, right? But it turns out we don't need it, because if you really think of the likelihood is not only, or the log likelihood is not only the exponent of the Gaussian, but there's also a term that comes from the partition function of the Gaussian. So if you increase the variance, that also means you basically lower the density everywhere, and so you get penalized for that. And by basically appropriately trading off mean against variance, your network can basically learn to judge its uncertainty. If it knows that it's correct, it should output a small variance, because if the variance is small, then basically this small distance will be rewarded. But if the network is off, then you want to output a large variance, because then you have a large distance here, and you want to mitigate that. Okay? So you don't need an additional supervision signal, just the log likelihood, and that automatically takes care of it.
What is the log likelihood here? I still don't get it.
So what is the log likelihood? Well, you just basically, right? What I argued is that you're assuming that the network output is some distribution as represented by some parametric family. Okay? And now the actual thing that the network is predicting are the parameters, but we think of it as predicting a distribution over the output variables y. Okay?
Beginning, how would you know it's a distribution? You have
It's an assumption.
example. You have an example of input and output pair. So where is the distribution? I guess I was just lost.
We're basically assuming the same distribution as we would do when we do supervised training with a certain loss function. So if we basically normally would train the network using an L2 loss, we take the equivalent Gaussian distribution, as was alluded to earlier. We simply make that assumption that the output distribution is Gaussian, and now we try to find the right mean and the right variance for it. Or if in the other setting we wanted to predict, say, an L1, then we basically
If you have
use
input and output, how did you get that
The
distribution?
target is still a delta. The target is still just a point, like the number 5. It's just that if the network can actually learn to predict 5, if you give it a mean, maybe it'll predicts 4. For this example, it can have increased variance. So
Right.
the loss will go down.
Maybe I still didn't follow. I see it off now. Otherwise, I delayed the lecture.
no problem. I can try to explain it again. So you're outputting the mean and the variance, and then you score it with the likelihood. And if you score it with the likelihood, then you basically have two terms. You have the traditional error term, but the error term is scaled by the variance output. And now the variance gets tuned because it needs to relate to the error that the network is making on the specific output. Does it make it clearer? Okay. Results I'll get to in a moment. Before I get there, I want to talk about this alternative path that I mentioned, which is to not simply output a distribution at the last layer, but to assume, well, if we're talking about aleatoric uncertainty, that means we have some uncertainty in the input, but somehow we didn't take that into account so far. So what if we assume that we already have an uncertain input, and then we see what happens with the output distribution? And it turns out if we assume that we have an uncertain input, we don't actually need to add any parameters to the network. The uncertainty in the output falls out immediately. Okay? But for that, we need to sort of think of our network as working in a bit of a different way. So let's assume the following. Assume that we have some input uncertainty. So our observation X that we're making, I'm going to call for conciseness of notation, I'm going to call that Z0. So the activation at the 0th layer. And I'm assuming that this is distributed a Gaussian distribution, okay, with a certain mean around the true activation, and with the mean being the true activation and a certain variance around it. And that's a pretty sensible thing because we have, for example, sensor noise. Okay? And now I need to think about how I model every layer now in the network in this fashion. And what I suggest is that we can think of it as being every layer as being one edge in a directed graphical model where we have an activation coming in from the previous layer I-1, and we want to get a distribution over the activations at the ith layer. And our network being deterministic means that I simply take our input, feed it into our nonlinear layer, and then center a Dirac delta at the output. Okay? So that's how I would model a deterministic network. Okay? But now if I regard the input as uncertain, it means that even if every relationship between the layers is deterministic because I don't have a Bayesian network, but I rather do a deterministic transformation of my previous layer, I still get a distribution over outputs. Okay, so even if I have a deterministic rule going between every layer, if I have a distribution over different inputs, I also have a distribution over different outputs. Okay, that makes sense? Okay, so problem is, if I do that, that's sort of the basic assumption that I'm making. I'm getting a joint probability over all of the activations. So I have my input, a distribution, input uncertainty, and then I have my activations for the layers, and it simply factorizes like a chain network. Okay. So the problem is, even if the input activation distribution is Gaussian and is really simple, like camera noise, which I can approximate as Gaussian, after the first nonlinear layer, the distribution is no longer Gaussian. It's multimodal and complicated. Okay? And so how would I even represent that? That's difficult. So I might need to approximate this because at every layer, the distribution is only going to become more complex. So what we suggest is that, well, we can use actually the tools that we have from the graphical models literature, and their variational inference, expectation propagation, and the like are very popular tools for approximating families of complicated distributions. Okay, so what I want to do is what's called assumed density filtering, which is a specific type of variational approximation. I'm assuming that my overall activation distributions can be approximated by a simple factorized distribution over the different layer activations, where each layer activation is approximated as a Gaussian distribution. Okay, I know that it's a multimodal distribution, but I don't know how to represent it, so I'm assuming that every layer has a Gaussian activation distribution. Okay, and now the question is, can I find the right mean and variance parameter of that activation distribution? And it turns out one way to do this is basically, like in many variational approximation algorithms, you minimize the KL divergence between the true distribution and the distribution that I can represent, say my Gaussian here. And the way we do this is iteratively minimize that distribution. Okay, so we start at the input and then go to the first layer, second layer, third layer. Okay, so it's a bit abstract maybe, but it's going to become concrete, and I'll give you very specific rules for how to implement that in a normal network. So assume for now that we already have an approximation up until layer I-1. So we've already have an approximation over these variation distributions Q up until the previous layer. And now we want to add in what the next nonlinear layer is doing to our distribution and approximate that. Okay? It turns out the way we do this is we basically minimize the KL divergence between this distribution here and what we can represent in our variational distribution. And oops, sorry, I went too fast. So we want to minimize basically the KL divergence between these two with respect to the variational distribution. And it turns out what that means in the assumed density filtering context is that we simply need to do moment matching. Okay? So as Minka showed, if you basically do layer-wise in this case, or well, in a graphical model, if you know, starting from one specific node going out, you would do variational approximations. using assumed density filtering, you basically need to do moment matching if you use an exponential family distribution as the variational distribution, and we use a Gaussian, so that means we need to determine the mean activation and the variance of activations at every layer. Okay? So we take the multimodal activations that we have and we try to find its mean and its variance, and then we go to the next layer. Okay? So even if the overall thing may seem complicated, ultimately what we need to do at every layer, we just need to find the mean and the variance of the activations. Okay? So the question is, how do we do that? So keep in mind, what we assume is that we have an uncertain input, so the distribution over the inputs is Gaussian, and then at every layer we're computing the best Gaussian approximation to what the network does to this input distribution. Okay? So let's see what happens with the typical layers we have in a modern neural network. Okay? So the simplest layer we have is a linear layer. A linear layer just takes my previous activations, multiplies them with some matrix W, and adds a bias into it, and if I'm assuming that my previous layer Zi-1 was Gaussian distributed, I can ask, well, what's the distribution of my next layer? And it turns out linear transformation of a Gaussian is a Gaussian with linearly transformed mean, and the variance is also simply related to that matrix W. And one important observation to keep in mind is that if I do that, and I compute mean and variance of the activations, those are actually two separate paths through the network, at least in this linear layer, because as you see, the variance does not play a role in determining the mean or vice versa. Okay? But those are linear layers. If our network only had linear layers, it wouldn't be very powerful, so we need a nonlinearity. So the most common nonlinearity are the rectified linear units. And it turns out, even in the 90s already, Hinton and Garamani looked at rectified Gaussians and how we can represent them. And it turns out we can actually compute the mean and the variance of a rectified Gaussian in closed form. Okay, I don't want to derive this and explain the equation in detail. You just need basically the Gaussian density and the cumulative distribution function of a Gaussian, and then you can directly compute the mean and the variance of the activation. Okay, so fairly simple. As opposed to just doing the ReLU, you basically apply these two rules and store the mean and the variance of the activation after the ReLU. Okay, so that's fairly simple. Now you don't have only ReLUs, you might also have leaky ReLUs, parametric ReLUs, where basically you have two linear pieces but with different slope, slope 1 on the positive half space and some smaller slope in the negative half space. And it turns out a leaky ReLU is just a linear combination of two ReLUs. Okay, and if I can compute the mean and the variance of a ReLU, I can also compute the mean and the variance of a linear combination of two ReLUs. So even for the leaky ReLU, I can compute the mean and the variance in closed form. Okay, so the point of the story is, for many components here in the network, I can, instead of simply describing how they apply to the activation, I can now describe very simple computational rules that tell me what are the mean and the variance after applying that specific layer. Okay, if the previous layer was Gaussian. The other nonlinearity that we typically have in networks is max pooling, and there the beauty ends a little bit because there's no closed form solution for the approximation to the mean and variance of the maximum of two Gaussian random variables. But it turns out it can still be approximated quite well. Again, I'm not going to describe the formula. So there's a very good approximation for the maximum of two Gaussian random variables and the mean and the variance of it. And in max pooling, I don't just, of course, want to take the maximum of two Gaussian random variables, but I want to take the maximum in a 2x2 block. But it turns out, as Jin and colleagues proposed, that can be taken care of by basically maximizing first pairs and then taking the maximum of the two pairs. And then I have the maximum in the entire 2x2 block, or an approximation thereof. Okay? So to summarize, I'm assuming that my input is uncertain. It has some Gaussian distribution with some variance. Then I'm going layer by layer, and at every layer I'm taking the nonlinear transformation of that Gaussian distribution and approximating it again with the Gaussian distribution by finding the mean and the variance of that activation distribution. Hold on a second. And I have a recipe basically to convert regular layers, linear layers, max pooling, ReLUs, parametric ReLUs, and basically do this computation. Yes, question?
Does this consider the covariance between different activations? Because there will be like extremely big, right?
Right, so the question was, does it look into the covariance between different activations? No, right? You just model a diagonal covariance, if you will, so individual variances of the nodes. Right, otherwise it would be infeasible. Okay, so what does that mean? So I told you this should be no engineering. It seemed like there were complicated formulae, but it turns out, though, you basically just can write drop-in replacements for your layers. So for your linear, ReLU, and max pooling layer, you basically just have an equivalent layer that outputs mean and variance, okay, and otherwise does nothing else. We've implemented that in different frameworks, and training proceeds by maximum conditional likelihood just as before, okay? So the only change is you regard the input as uncertain, you swap out your layer implementation for something that's a little bit different because it doesn't just apply the nonlinear transformation, but it computes the mean and the variance of that nonlinear transformation, assuming that the previous layer was Gaussian. And then you score the output distribution by means of conditional likelihood. Okay? So does that work? Okay? So I mentioned I want to talk about regression first. So here's a regression task, motion estimation, overlaid inputs. This is what we'd like to get out. This is what we get out with a standard flownet, which again is not state of the art anymore, but that's not the point here. The point is that it makes some error. When we now look at the uncertainties that the network produces with this method, then they're actually very highly correlated to the error that you're making. And you can see the visual similarity between those uncertainty maps and the actual error. Okay? And now I have two different rows here in my visualization. The lower one is if I simply use a probabilistic output layer, which is just meaning I only turn the last layer into a probability distribution. And the first row is to use this assumed density filtering, so this local variational approximation where I propagate the uncertainty through the network. Okay? So let's look at it a bit more quantitatively. So what I have here is first the accuracy, right? So that's a bit of a weird point, right? I mean, we want to get uncertainties, but we don't want to give up on our predictive accuracy, ideally. Otherwise, people are going to be unhappy because they want the benchmarks to work out well. It turns out that the accuracy actually doesn't really suffer very much. So this is the endpoint error where lower is better. And it turns out the probabilistic versions, which are highlighted here, are about as accurate with minor deviations, sometimes a little bit more accurate, sometimes a little bit less accurate than the deterministic version. Okay? And it turns out the dropout version is also similar in terms of accuracy. Okay? So you can, of course, always do test time dropout, like I mentioned earlier. The problem with test time dropout is now this. Whereas the regular network is real time, it runs at 106 frames per second. The dropout version, because we need, I don't know, to run through the network 30 times to get a proper distribution over outputs, we only get 3 frames per second out of this dropout network. So the deterministic approximation that we do is much faster. So the assumed density filtering gets about a 3 times slowdown, not quite. And the prob-out version is basically almost as fast as the deterministic network. Okay, so it doesn't occur a very big computational overhead. But what about the uncertainties? Are they good? It turns out they're actually quite a bit more accurate than the ones you would get with test time dropout. So these are log likelihoods. And one important observation that you can make is that the assumed density filtering version, where you propagate the uncertainties from the input through the entire network, is actually a lot more accurate than when we simply regard the last layer as outputting a probability distribution. Okay? And if I now look at the uncertainty and graph that against the endpoint error that I'm making, I see a very nice correlation. So the large errors happen where I also have high uncertainty, and the small errors occur where I have low uncertainty. So I achieve exactly that desired effect. that the uncertainty is very well correlated to the actual error the network is making. Okay, question?
So we didn't see this graph of flow, right? We saw it for Alex network, right? So
Yes, for classification, yes.
yeah, but even for FlowNet, we see without uncertainty modeling, do we see the school graph?
So this is not exactly the same graph that we showed before. So the diagonal is not necessarily the optimum point here. But that's a good question, right? So you can, of course, ask the same question that I asked with calibration, and I actually don't have an answer yet to that question. But yes, that's a fair point. I don't have the regular FlowNet for comparison because the regular FlowNet doesn't output any distribution, right? So I can't give you a plot because it doesn't have an uncertainty output at all. Okay, it only gives you a point estimate. Okay, so that's regression. How are we doing time? Yeah, okay. So what about classification? I mean, classification is also important, and as we mentioned, there's one problem with the regular softmax is that it tends to be very highly peaked and focused on certain classes, even if they're incorrect. Okay, and one way we thought about this is one problem in the softmax is that it doesn't really have a good way of sort of copping out and saying, okay, I think I have a certain preference for a certain class, but I don't really know how sure I am in my prediction. But it turns out there is a way to think of that. So you might have come across the Dirichlet distribution. And the Dirichlet distribution is basically a distribution over categorical distributions. So suppose I had 3 classes, and I want to output a certain preference for a certain class, then I'm somewhere in the simplex, right? Suppose this class here, I'm pretty confident that I'm this particular class, then I would predict a point in that corner. Now, if I'm not confident about my prediction, I might want to model the fact that I'm not exactly at this point in the simplex, but in some vicinity of that simplex. And it turns out the Dirichlet distribution allows you to model that. It allows you to say, well, I'm somewhere in the simplex, or I'm pretty sure we are in a specific region of the simplex. Okay? So we basically approach the classification problem a little bit different. We don't want to output the label, but we want to output a distribution over the labels, and we use the class probabilities as the learning target. Okay? So basically the last layer of our network is now a network that outputs a Dirichlet distribution. And the question is how you parameterize that. Okay? So what we propose is to basically use a standard softmax to basically give us the center of the Dirichlet parameter, and then the concentration parameter of the Dirichlet, which basically corresponds to this notion of variance. We basically get out of the variances of the previous layers. Okay, so we have this step that we call variance pooling, where we just basically take the variances from the previous layer, we weigh them with the softmax activations, and that gives us this concentration parameter. Okay, and so we output again a distribution, but it's a Dirichlet distribution, and then we use log likelihood training with the Dirichlet distribution, and use that as the training target. So we train with conditional likelihood as before, but now we want to score the distributional output rather than the probability of the true bin. Okay, so that's the difference to the classical setting. So what does that give us? So again, the important question is, does it hurt predictive accuracy? Right? Getting the uncertainties right is nice and all, but we kind of don't want to get worse classification results. With the previous temperature scaling method that I presented you, there was no change in classification accuracy. Here it might occur because we have a different learning target. We now want to score the entire distribution. And it turns out with both variants of our network, with this assumed density filtering and the probabilistic output layers, we get fairly good accuracy on standard networks with standard data sets. Okay? But the question is, do we get a good agreement between the uncertainty and the error that we're making? Now, this is unfortunately a different type of plot than the one that I showed you earlier. I now plot the entropy against the cross entropy. But here you see the differences between the softmax, where you don't have a clear agreement between the entropy of the categorical distribution and the cross entropy of the holdout or test data. Whereas with the Dirichlet output layer, you get a very nice relationship between the predicted uncertainty and the actual accuracy of the data set. Okay, question?
So, in principle, you could have done the same thing with the softmax as well, right? And calibrating the temperature. Or no, it's...
yeah, so that's a good question. Sorry?
It's like the concentration parameter for the Dirichlet distribution.
That's a good question. That's a good question. I would need to think about that, but yeah, in some sense it's true. You might be able to do that with but then that would actually relate to the earlier idea
I've done that in semantic segmentation experiments. So just the output also includes the temperature, because it's differential will affect the temperature.
Okay.
But so it's a function of the input. So for each example, you have different temperature.
Yes, and so in our case that happens as well, because that a concentration parameter which would relate to the temperature is also being predicted by the network. Here it falls out of the activation distribution. So I guess it's a bit, so your case would be more like you're having an additional output that you're regressing against, right?
Yeah, so like you have whatever classes, and then like for this k, you just have a k plus 1
Yes,
parameter.
okay,
And
yeah.
so just for whatever example you use it on, it'll just flatten the distribution.
Mm-hmm. Yeah, okay, that's a good question. So we haven't compared against that. But that's an interesting question, yes. I cannot give an answer right now, but there might be definitely some relation here. Okay, so that's accuracy, uncertainty. So what happens to the distribution? So let's look at a couple of examples. So here's examples where we correctly classify. And so here in red is the typical softmax with the usual thing that often it's very confident, but actually to be in all fairness, the softmax isn't always so super confident. On this example in CIFAR, it actually knows that it's a bit unclear what it is. And so it has high confidences for different four-legged animals and the biggest confidence for deer, okay? And it turns out the general trend that we observe with the Dirichlet trained network is that it hedges its bets a little bit. It doesn't bet only on one class, but it spreads out its bets a little bit more. But that not evenly. In incorrectly classified examples, it tends to spread out its bets a lot more than in correctly classified examples. Okay, whereas the standard softmax tends to still be very confident. Okay. Of course, that doesn't mean it always works. There's also failure cases. So the Dirichlet layer, of course, also gets incorrect classifications. Here it outputs bird, whereas the ground truth is horse. But of course, the same happens for the softmax. The difference, again, being the softmax, even in failure cases, is really, really confident. The Dirichlet, even if it messes up, it tends to output a relatively broad distribution. Okay. So you at least get some sense of when you don't know. Okay. So in the beginning I said I don't want to talk about adversarial attacks, except that I do very briefly, because it turns out one somewhat strange and so unexplored side effect is that this also increases the robustness to adversarial attacks. So this is a standard fast gradient sign attack, and this is the classification accuracy as plotted with different, or as evaluated with different attack strengths. And it turns out that, so here the first row is basically our standard deterministic network with cross entropy. And then if I use these probabilistic output layers, it turns out they're quite a bit more robust to adversarial attacks. Okay, but even though we didn't specifically train for that, somehow the distributions seem to induce that, and I think more work is needed to really understand that. So to wrap up, that part. So I presented you a lightweight treatment of probabilities in supervised learning. That's not to say unsupervised learning isn't important. It's very important, but supervised learning still dominates our current literature. I tried to tell you that we can basically use these probabilistic output layers that are sometimes used in 3D reconstruction, and they work out quite well, also for other problems, and I highly encourage you to try them out. Propagating the uncertainty all the way through the network works even better for getting calibrated uncertainties, but it has a certain computational overhead, which is fairly small. And we can apply this technique both for regression, where we can use this power exponential layer to be the equivalent of the various types of LP losses that we often use, and for classification we can use a Dirichlet layer to represent the uncertainty over the categorical distribution. So we get fast and reliable uncertainty, yet we retain the predictive power, which is always important, I think, and it's faster than a sampling-based approach. We only need to do one forward pass through the network, maximum about a 3 times slowdown, but still fairly little, and we get a very high correlation between the empirical error induced by the network predictions. So to sum up a bit more broadly, I tried to tell you that standard supervised deep networks don't yield good uncertainties, especially in the calibration case where the distribution is highly miscalibrated. And in regression, we don't get any uncertainty at all in 99% of the cases that we see today. But there's a number of solutions, and there's many more. I only presented you the ones that I regard as highly practical. Temperature rescaling is probably the simplest method to tackle calibration errors in classification. If you have a regression type problem and you really also want to get at the epistemic uncertainty of the problem, test time dropout works quite well. But it's easily outperformed by variational approximations. However, they get somewhat more complicated to implement. Still fairly easy because you just need to do a drop-in replacement of your layers, and otherwise you don't need to change your network at all. And intermediate between the two are ensembling methods that are fast test time dropout, but you need to adapt your network if you want to get it really fast. I think much more work is needed if we want uncertainty in our computer vision applications, because especially the epistemic uncertainty requires completely different network architectures, and the ones that we see in the machine learning literature, they're not really practical enough yet for our very big networks that we use in computer vision. Okay, so now I have 5 minutes left, and I still want to do the obligatory overview about some projects, recent projects that we're excited about, and there's no relation to what I talked about previously, so this is pure advertising, just to wrap it up, and then I'll shut up for today. So one thing that we presented at CVPR that I quite like is we basically showed how to make high capacity networks smaller without actually adversely affecting the accuracy. In particular, we looked at optical flow estimation. And one thing that you see in several applications is that people use multi-stage architectures. And it turns out we showed that you can actually use weight sharing between these stages, and not only in this example, but also in a bit more elaborate examples. And the benefit of this is that you shave off a lot of parameters, up to 60% of the parameters of your network. And so you might think, okay, well, if I use fewer parameters, then I'm going to mess up the accuracy. It turns out the opposite is the case. On data set, the accuracy stays the same, and off data set, the accuracy gets quite a bit better. Okay, which may seem counterintuitive, but you just give the network less chance to overfit. And for me, there was an interesting insight that we should really not simply throw as many parameters as we can get, as we can have at the problem, but really think carefully about being frugal about the parameters, because it really helps with off-data set generalization. So for example, in the flow case, we have this traditional problem that we often need to train on synthetic data, and then on real data it works less well. If we make our network very compact and concise, that problem becomes much less severe. Okay? So that was at CVPR with my student Junhua Huer. The next completely unrelated thing that I wanted to briefly tell you about, so that you could look it up if you're interested, is this question of instance segmentation. So instance segmentation is very nice, but the pipelines that we see today are very much unlike, in some sense, how a human would describe a scene. So if I ask one of you to describe what's in the scene, okay, there are lots of cars here, but if you were to point to a car, you wouldn't point at the one here in the back, but rather to one that's in the front. And similarly, when we describe a more complex scene, we would tend to describe the dominant objects in the scene first rather than something in the background that's not very important. Yet in the typical instance segmentation architectures, we output either all instances at once, or even in the recurrent architectures, they're somehow not forced to explain the scene in a way that's somehow sensible from a human perspective. So what we asked is the question, can we, in a recurrent fashion, segment a scene into different instances so that our first segment, the things are obvious, and only then get to the complicated bits? Okay, and it turns out you can actually formulate this as a reinforcement learning problem with an actor-critic model, where we basically just use the standard supervised objective, but we don't actually specify the order in which we shall segment the scene. And the thing that pops out directly from that is that the network learns to segment these big chunky objects first and then uses them as context for the more difficult semi-occluded objects. There's, at least evidentially, there seems to be a good agreement with how we humans might segment or describe a scene. We are very curious to look into that more from the human vision perspective. We haven't done that, but this is work that I'm quite excited about. And the last thing, and then I'm done, again, totally unrelated, but also work that I quite like, and I wanted to briefly advertise. My student Tobias Plötz and I have worried about this problem that convolutional layers, they act quite locally, right? And we all want to increase the size of the receptive field. Dilated convolutions are one way to do that. But in specific areas of computer vision, for example, in image restoration, this principle of non-local feature aggregation is proven really powerful. So in order to make a prediction about a small patch, you don't just want to look at the evidence from that patch and from the surrounds, but you want to look at similar patches in the input and somehow aggregate the information you have there. But we don't seem to have anything like that in our convolutional networks. So what we proposed is a non-local layer for networks where, similar like in these non-local image methods, you try to find the k nearest neighbors in the image plane and aggregate basically the patches from there. Okay? And I'm not going to describe to you how we do this, but we basically have a end-to-end trainable way of retrieving k nearest neighbors. And that means you can do, you can basically non-locally combine information, get a really big receptive field without having many convolutional layers. Okay? And that has applications, for example, in restoration, but not only, beyond that as well. So that was my advertisement block. Now I'm finishing right on time. I have 10 seconds left. Very good. Thank you for your attention, and I'm happy to take a few more questions.